To understand the Black Scholes model, we must first look at how we model share prices in continuous time. Unlike discrete models that jump in steps, we assume the share price, denoted as S sub t, evolves according to a stochastic differential equation, or SDE. Specifically, the change in the share price, ds sub t, is equal to mu times S sub t, dt, plus sigma times S sub t, dz sub t. In this equation, mu represents the drift or the expected return, while sigma represents the volatility of the share. The term dz sub t represents a standard Brownian motion, which introduces the element of randomness into the market. This framework defines what we call geometric Brownian motion, implying that while the returns are normally distributed, the share prices themselves follow a log-normal distribution. This ensures that share prices remain positive, which is a fundamental requirement for any realistic financial model. Now let's look at the solution to our SDE. We can express the share price at any time t as S sub 0 multiplied by the exponential of the quantity, mu minus sigma squared over 2, all times t, plus sigma times z sub t. To verify this solution, we apply Ito's lemma, which is essentially the version of the chain rule used for stochastic calculus. By taking the partial derivatives with respect to time and the Brownian motion, we can confirm that our exponential expression perfectly matches the original SDE. Because the Brownian motion z sub t is normally distributed, the natural log of the share price is also normally distributed. This means the share price has a log-normal distribution with a mean and variance that scale with time, allowing us to calculate the probability of the share price landing within a certain range at maturity. The Black Scholes formula itself provides a closed-form solution for the price of European options. For a call option with strike price K and maturity T, the price is the current share price times the cumulative normal distribution of D1 minus the discounted strike price times the cumulative normal distribution of D2. Here, D1 and D2 are standardized variables that account for the time to maturity, the risk-free rate, and the volatility. We can think of the cumulative distribution of D2 as the risk-neutral probability that the option will expire in the money. If we need to find the price of a put option instead, we don't need to start from scratch. By using put-call parity, we can derive a similar formula where the put price is the discounted strike price times the cumulative normal of negative D2 minus the share price times the cumulative normal of negative D1. The true elegance of the Black Scholes model lies in the PDE approach, which relies on the concept of a risk-free portfolio. Imagine we create a portfolio by selling one derivative and buying a specific number of shares, often called the delta. By choosing the number of shares to be the partial derivative of the option price with respect to the share price, we can actually cancel out the randomness from the Brownian motion. This process is known as delta hedging. Since the resulting portfolio has no risk over a very small time interval, it must earn the risk-free rate of interest to prevent arbitrage. This leads us to the Black Scholes partial differential equation, which must be satisfied by any derivative whose value depends on the underlying share price. Crucially, you'll notice that the drift parameter, mu, disappears from the final pricing formula, showing that the option price depends on the risk-free rate and volatility rather than the expected return of the stock.